Hello, I'm Brad Duerstock. I'm from the Weldon School of Biomedical Engineering and the School of Industrial Engineering at Purdue. Today I'm going to talk about machine learning for AT development. This is definitely an area of interest among a lot of groups. For instance, the Microsoft AI for Accessibility project, as well as other programs. So today I'm going to talk about how we implement machine learning in some of our AT development. And the whole idea is hopefully to spark some interest in how machine learning can be used and to really broaden this field. Right now, there are several technologies that have been incorporating machine learning for some time that have been very beneficial to people with disabilities. First is the Amazon Alexa that uses natural language processing to allow us to more intuitively or naturally communicate with Alexa instead of using specific command words. The universal recognition of speech recognition programs and recognition programs like through Siri have also been a tremendous value compared to having to train a program yourself based on your own unique profiles. Face and object recognition apps have really benefited the blind, and using wearable technologies can help understand, detect unique medical conditions for individuals. So, those are some of the technologies that incorporate machine learning principles. To kind of start at the same page, I just want to kind of present these ideas regarding machine learning. It does a great job at recognizing and classifying data sets, usually trained using big data or deep learning. And then machine learning models can make predictions based on this trained information. And lastly, it can continue to learn or be better trained as new data is provided. However, machine learning cannot identify relationships that are not present in the data. So data veracity is still very much needed. Nor can machine learning models replace the need for standard statistical analysis or the need to conduct randomized control trials. To give an example of how we incorporated machine learning principles as an assistive technology is the use of hand gesture recognition. It's becoming a popular method of using controlling devices or interacting with the computer environment, also as a way of rehabilitative therapy through video exercise. This is something that we've been very interested in. Unfortunately, the commercial gesture recognition systems have really been trained by people without disabilities. So, someone with a high level spinal cord injury, Parkinsonian disorder, or muscular dystrophy, whatever, they have unique mobility differences, and their movements are not going to be accurately recognized by these commercial systems. So we are then forced to create our own gesture sets for these types of individuals with upper limb mobility impairments. Well, this can be very time consuming, very costly. And then you have the added challenge of how to apply these new gesture lexicons for persons with spinal cord injury to a rehab therapy game or to a computer system or for controlling a robot. So we decided to look at this problem from a different angle. What we did was we took a standard gesture set, such as for Xbox and Wii or Windows. We took these commands and then we looked at the unique features of movements using Laban theory of movement for a group of individuals with upper limb mobility impairments, which is tetraplegics due to spinal cord injury. We're able to find unique differences that were shared among this population of users. Then taking these features, we were able to then modify automatically or transform this standard gesture set to a whole new constrained gesture set or lexicon of gestures that are highly recognizable for tetraplegics. So, for instance, we have a top row, we have standard gestures, A through G, typical gestures, lexicon, and then we have the translated gestures for tetraplegics due to spinal cord injury. As you can see, the lines are more curved for tetraplegics, doing that specific gesture. If you're doing a circle in the air, it's going to be more oval or lopsided. So we could create a lexicon based on these idiosyncratic movements of this group of individuals to create a whole new gesture set that could then be reintegrated into existing programs that recognize these standard gestures. Now, going one step further with gesture recognition, in this case, it was an application really geared toward rehabilitative therapy, where one has to move constantly to perform some type of gameplay action that has a therapeutic benefit. The challenge we were trying to overcome is how to discriminate intentional from non intentional movements, or the Midas touch problem. With speech recognition programs and gesture recognition programs, you usually have some type of a cue. For Siri, it's "Hey Siri." Then it recognizes what you're going to say next, or you say Alexa to get its attention. With gesture recognition, it's usually some type of switch. Well, in this application of a rehabilitative therapy, it's not practical to have to hit a switch when you're in the middle of gameplay. So I had to look at the system to devise another way of automatically looking at the differences of or be able to discriminate intentional from non-intentional movements. And so this video shows an individual performing some type of gesture task. On the right, we see all these movements in this big spaghetti ball of movements. And based on differences in velocity, we were able to segment intentional gestures from non intentional movements. And then using kernel density estimation and K means algorithms, we could then cluster or look at what are the high frequency of intentional movements, where are they located in 3D space? And then the practical implications are then what we can understand now what individuals are moving, how frequently, what are areas of comfort, or maybe where are areas that need to be to motivate people to go to increase their mobility as a therapeutic benefit. The second example I'm going to talk about of where we use machine learning for AT development is the use or the development of a multisensory substitution system for digital images in real time. As you can see in this video, there's a haptic controller that allows the individual to interrogate this digital image on the screen. They're getting feedback, both force feedback from the haptics as well as auditory responses and different vibrotactile responses through tactors. This system is very good at allowing someone who is blind be able to perceive an image. It's actually more adequate, more depth of information in terms of color, intensity, shapes, and size and position of objects than using a tactile printout. However, it does take some training and can be more time consuming. So we wanted to see how we could make the system more efficient with machine learning. Well, we discovered that the exploratory procedures of using the system really fell into five different categories. And since we know these are the common exploratory procedures, we could then build a neural network. Again, it's very complicated, a lot of data that you can include, and the more data, the better. And this model neural network could then understand and predict what that user is doing as they are interrogating this image in real time. That is great, that capability, but we really wanted to assist the users to be more efficient. And so, using this neural network, we could understand their behaviors and then automatically provide some type of intelligent assistance while they're exploring the image. And this automatic feedback could be a way of allowing the system to say, hey, you're close to the edge, or to understand when you're looking at one, or in this case, blood cell, that it's close to the edge of the image or to other cells or its approximate location within the entire image. And this is where the really efficiency comes into play, is to be provide the correct feedback or assistance during the time when the user needs it, almost simulating having someone sit next to you who is sighted and say, hey, this is where you're located, and this is the type of image you're looking at, and to provide that assistance. But now it can be done, performed independently. So I'm going to leave it there. I hope this has been useful. In conclusion, here are some tips I have on machine learning for AT development. AT machine learning can help recognize users' behaviors, can help them in the decision making process, and provide some assistance to be more independent or efficient without needing that extra help from human assistance. Machine learning is not necessarily AI, which is really aimed at getting computers to think like we do. However, machine learning does allow us to see things that are not always apparent, be able to see through that clutter of data. We really need to also advocate with tech companies who are developing machine learning models and data sets to incorporate information from people with disabilities, whether it's movements or physiological data, so that it becomes part of that understanding of recognition of, okay, this is not just people without disabilities, but there are some people who do things a little bit differently. Because as we know, persons with disabilities do not fit a one size all design parameters. So there also needs to be an allowance or a procedure to allow machine learning to understand or adapt to people with disabilities for a more personal or more effective experience. And lastly, as kind of a word of caution, as we are beginning to naturally communicate with AT in a more human way, in a more effective way. And as we incorporate them in our homes, such as voice assistants, Google or Alexa, or even collaborative robots, that inadvertent or accidental activation is going to happen. So we need to think of that, of how we can look at these type of challenges. Again, I thank you for your attention and look forward to having more discussions during the conference.